In this video, I'll be going through the 2020 scholarship physics paper. Question 1. A capacitor, ideal inductor, and 12 ohm resistor are connected in series to a 6.5 volt variable frequency power supply. State the conditions for resonance in a circuit of this type and describe what you could measure to determine when resonance has been reached. And so we can make a number of mathematical statements as to what happens at resonance. Let's start with the fact that our inductor reactance equals our capacitor reactance. And since our total reactance is just our XL minus XC, given that these two are equal, that means our total reactance is 0. Now, as for our impedance, it's given by this equation here. And since our reactance is 0, our X here just cancels out, and we're left with our impedance is equal to R, just our resistance, which we know from up here is just our 12 ohms. And so, of course, this means that our impedance is at a minimum, which means that our current is at a maximum. Now, as for what we can measure, our above conditions have some interesting implications for our voltages. So we know that the voltage across our inductor is the current times our reactance of the inductor. Now, since this is a series circuit, the current is going to be the same through all components. And since we know that the capacitor reactance is the same as our inductor reactance, we can also write this, which happens to be the equation for the voltage across our capacitor. Thus, the capacitor and inductor voltages are equal. And now the source voltage is the vector sum of the component voltages in our circuit, described by this equation here, where our inductor and our capacitor voltages, of course, act in opposition. If you like, you can view this equation as a consequence of our inductance. Or perhaps this derives the other, whichever way you want to look at it. Now, given that our voltage across our inductor and our voltage across the capacitor are equal, this equation, of course, becomes the square root of VR squared, which of course just gives us VR, meaning that the source and resistor voltages are equal. So we've provided two separate measurements that can be performed to verify that the circuit is indeed at resonance. If a circuit like this is at or near resonance, is it possible for both the inductor RMS voltage and the capacitor RMS voltage to exceed the RMS voltage of the power supply? Explain how this can occur. And so we know that the voltage of our source is equal to the voltage of our resistor, which is in turn equal to the current times the resistance. We also know that the voltage of our inductor, which is equal to our current times our XL, is also equal to the current times our XC, which is the voltage across our capacitor. These are things we just went over in the previous question. Now, what we can see here is that because the current is the same at all points in a series circuit, if our reactances here, which are equal, exceed our resistance, then our voltages here, which are also equal, will exceed the voltage of our source. If XL and XC are larger than R, VL and VC will be larger than VS. The frequency of the power supply is adjusted, while the supply voltage remains constant at 6.5 VRMS. When the frequency of the supply is 134 Hz, the current in the circuit is 0.4 amps RMS. The supply frequency is then increased and the current changes, but at 199 Hz, the current in the circuit is again 0.4 amps RMS. None of the components are changed while this occurs. explain how it is possible to have the same current in the circuit at two different frequencies. And so for an LCR circuit, resonance occurs at our resonant frequency right here, which represents a maximum in current. Since this is a maximum, our current is symmetrical about this line, which means that our 0.4 amps is going to be somewhere like here, which means that our 134 Hz is going to be here, and our 199 here. Now, the reason we have this shape of distribution at all is because the frequency dependence of our capacitance and inductor reactances are inverse to each other. Meaning that if you increase our frequency, our capacitance reactance goes down, whereas our inductor reactance goes up. And because our total reactance is XL minus XC, we have one side where the capacitor reactance dominates, but as frequency increases, it decreases and XL increases to the point where they are equal, at which point we have no total reactance at all, and then the reactance of our inductor dominates, and our total reactance increases, leading to a reduction in current. So let's see if I can word that. Current reaches a maximum at the resonant frequency, forming a symmetrical distribution where 0.4 amps is achieved at both 134 Hz and 199 Hz. This maximum occurs due to the inverse dependencies on frequency between XL and XC. Calculate the values of the capacitance C and inductance L in the circuit. So we have two situations here. Our first is where the frequency is 134 Hz, and we'll call that F1. And now, given our angular frequency, this will come in handy later on, we know that is going to be 2 pi times 134 Hz, which gives me 841.9 radians per second. And so bearing in mind that our reactances are given by these equations here, at our lower frequency, our XC is going to be greater than our XL. And so the equation for our reactance can be given by XC minus XL. We'll return to that in a moment. Now, for our second frequency of 199 Hz, we can find our angular frequency, and that gives me 1 to 50 radians per second. Now, at this increased frequency, it is our XL that is going to be greater than our XC. Because as we increase our frequency, you might recall, our XC decreases, whereas when we increase our frequency here, our XL increases. So at a higher frequency, our XL is going to be larger. What that means is that our reactance can be written as XL minus XC, the opposite to our lower frequency. Now let us substitute our equations for our reactances. So what I'm going to do here is I'm going to solve both of these equations for L, which will let me then equate them to eliminate L altogether. That will allow me to solve these equations for C and find my capacitance. I can do that because I know our frequencies, and I can also find the reactance, since I know the resistance, current, and voltage. We'll figure that out later on. And so my first step is going to be to add omega-1L to both sides and subtract X from both sides, which will leave me with this. And now if I divide both sides by omega-1, I'll have solved it. Now let's solve the other frequency. For this, I'm going to swap the sides around and add 1 over omega-2 C to both sides. And now dividing both sides by omega 2. So now I'm going to equate both of these equations so I can find C. So taking this here and making it equal to this here, since we know that these L's are equal. So now I'm going to put the capacitor terms on the right side and the others on the left. You'll see why I'm doing that in a moment. I'm going to do that by adding x over omega 1 to both sides, then subtracting 1 over omega 2 squared c from both sides, and I'm also swapping them around. Hopefully you can follow. Now I'm going to multiply both sides by c, whereas c's on this side cancel out. Now I'm going to divide both sides by what I have in my brackets. I'm also going to make things a little bit easier on myself and rewrite our 1 over omega squared as omega to the power of minus 2. Hopefully you're familiar with that mathematics. Now, to go any further, we first need to find our reactance. Now, we know that our source voltage, which we know, is equal to our current, which we know, multiplied by our impedance, which we know some of the components of. Our impedance can be written as this. Where we know our resistance, that was 12, I believe, and we're trying to find our reactance. So we just need to solve this equation for the reactance. So I'm going to divide both sides by current and square both sides. Then I'm going to subtract r squared from both sides. Then I'm going to square root. Doing all of that should give me this equation here. Putting my numbers in. That gives me 10.96 ohms. So let's put our numbers in over here then. Which gives me 3.54 times 10 to the minus 5, and our units are, of course, farads. Now, knowing our capacitance, we can now find our inductance. And we can do that by using either one of these equations, and why not, we'll choose this one here. Putting our numbers straight on in, which gives me 0.0268, and our units are, of course, henries. Question 2. For a moving source of sound, the frequency heard by a stationary observer can be calculated using the following equation. Explain the use of the plus-minus symbol in this equation. So this bottom term here gives us essentially the wave velocity relative to the source. Let me do a quick diagram. For the waves traveling in front of the source, which is moving in this direction here, because the source is moving with the wave, the relative velocity of the wave is going to be less. And so our relative wave velocity is going to be VW minus VS. An extreme case is if the source was traveling at VW, at the wave's velocity, then obviously the relative velocity of the wave is going to be 0. Now, as you might suspect, for the waves traveling behind the source, they are moving away. Their velocity is in the opposite direction to the source velocity, which means that their velocities add. So let's put that into words. VW plus or minus Vs represents the wave velocity relative to the source. For the wavefronts ahead, this is a minus. For the wavefronts behind, it is a plus. State the assumptions made about the velocity of the moving source of sound. So our assumption in this case is that the velocity of the source is directed completely towards the observer. In other words, we're assuming that the velocity of the source that we're using is the relative velocity between the observer and the source. We assume that the velocity of the source is directly towards or away from the observer. An object is moving in a circle with radius r at a constant speed vs while emitting sound with a constant frequency. At the instant the observer at point P hears the sound at maximum frequency, the source has reached the position indicated in the diagram. Show that this here is true. And so this angle that we're trying to show is the angle at which the source is at when its maximum frequency has reached point P. And so the sound heard at point P at the maximum frequency will have left the source when the velocity of the source was directed towards the point P. Or in other words, the tangent to this circle that also goes through the point P. Let me try and draw that. Now if we draw a line to the center of our circle here, the line to the center and the line tangent is going to form a right angle. So you might see here that we have a right angle triangle, which is usually quite handy. Now I'm going to call this angle here phi, which means that this angle here is 90 minus phi. So let me bring that triangle out to the side. And let's call the distance that the wave has to travel to get to point P capital D. And so my plan is to first find an equation for our starting angle, essentially, then add onto it the angle at which the source has moved through in the time required for the wave to travel this distance d. To do that, I first want to find an equation for my angle phi, our starting angle. Then I want to find an equation for the time, which we'll be able to do by using Pythagoras to find the distance and knowing that the velocity of the wave is just VW. Following that, we can just use some basic rotational mechanics to formulate an equation for the angle rotated through in that specific time. Bottom line is my first step is to find an equation for the angle phi. And so using our SOHCAHTOA, we have our hypotenuse here, we have our adjacent here, and we have our opposite there. And so I'm going to use our adjacent and hypotenuse sides so that we get an equation in terms of r and d, which are terms that are present in the final equation that we're looking for. And so the equation we're going to use is our CAR, which is that our cosine angle, which is 90 minus phi, is equal to our adjacent, which is our r, divided by our hypotenuse, which is our d. Now you may be aware that cosine of 90 minus an angle is quite simply just equal to sine of that angle. Taking the inverse sine of both sides, and there we go. Now my next step is that I want to find the time. To do that, I'm going to use an old favorite, that the velocity, or specifically the velocity of the wave, is equal to our distance divided by our time. Rearranging that. Now we want to replace our capital D, our distance, with variables that are present in our final equation. We can do that using a bit of Pythagoras. So looking at our triangle up here, we can state our Pythagorean formula, which is that d squared, our hypotenuse squared, is equal to r squared plus capital D squared. Solving that for d gives us the square root of d squared minus r squared. So let's make that substitution. Now let's find our total angle. So our total angle is going to equal the angle that's been rotated through in this specific time, and we can write that as omega t, where if you're scratching your head, you might recall that our angular frequency is equal to the angular displacement over time, rearranging that, gives us that the angle is equal to omega t, so we can write an angle as just omega t, plus our original angle phi, which we found over here, and which looks suspiciously familiar. Now, given that our final equation that we're trying to solve over here does not have omega in it, we need to replace that with something that does. Now, we have an equation that relates the linear velocity with the rotational velocity, and that is that our velocity is equal to r omega. And in this case, the velocity in question is the velocity of our source, which does not change. It is going at a constant speed as mentioned above. So we can replace our omega with, solving this equation, Vs over r. Now we can replace our t with our equation over here, and we can replace our phi with our equation over here. And what do you know? This here is the same as this here. The Doppler effect can also be observed when a moving observer approaches a stationary wave source at speed v0. The relationship for the apparent frequency f prime when an observer moving at speed v0 approaches a stationary source is given by this equation here. Explain when the observer would experience the greater Doppler shift, when the source approaches the stationary observer at speed v, or when the observer approaches the stationary source at the same speed v. And so at first glance, this might look like 6 of one, half a dozen of the other. But the two situations are distinctly different. In the first scenario where we have our familiar Doppler effect, we have a source approaching a stationary observer. The property being directly affected is the wavelength. The wavelength is being shortened ahead and lengthened behind. On the other hand, in our second scenario, where it's the observer approaching at a speed v, the property being directly affected is the relative velocities, specifically the relative velocity of the wave. A moving source shortens the wavelength ahead of it as it moves towards the last front it produced before producing another. A moving observer observes a greater relative wave velocity. The equation for a moving source is our familiar Doppler effect equation, and for an approaching source that is going to be a minus Vs. Now for our moving observer, we're given the equation above, where we'll just call our velocities V. Now, the best way to probe these equations definitively is to examine the scenario where the velocity is equal to the wave velocity. For our moving source, we approach what is essentially a divide by zero, which means that our observed frequency is approaching infinity. For our moving observer, our VWs cancel, and we're just left with twice the original frequency. And so we can see that the greater Doppler shift is experienced by the moving source. Question 3. We're given the mass of a neutron and also the definition of an electron volt. I'm sure that will come in handy later on. A slider S1 is moving along an air track at constant velocity v and collides elastically with a stationary identical slider S2 as shown in the diagram. Explain why S1 stops and S2 moves off with velocity v. This is a consequence of two things: conservation of kinetic energy, the fact that it's an elastic collision, as well as conservation of momentum. So let's bring those equations together and see what pops out. So let's start by saying that our initial kinetic energy, which is the kinetic energy of S1, where v is the initial velocity of S1, and m is the mass of S1 and separately S2, they're both identical, And that's equal to the kinetic energies of S1 and S2 afterwards, where V1 and V2 are the velocities of our sliders S1 and S2 respectively. We can divide our half mass out, which gives us this Pythagorean relationship here. Now let's consider the conservation of momentum. We know that the momentum before of S1 is equal to the sum of the momentums afterwards of S1 and S2. Dividing our mass out, which gives us this elegant equation. Substituting for V into here, with a little bit of thinking, we can see that this equation here will only work with two solutions. The first is that V1 equals 0 and V2 equals 1, and the second is the opposite. Now, because our second slider experiences a force in this direction, it has to move. We have to have a scenario where our second slider moves, which means that this solution isn't possible, and therefore we must have this one. As V2 experiences an unbalanced force, it must have velocity. Thus V1 equals 0 and V2 equals 1 is the only possible solution. Now, as a side note, 0, 0 is also a potential solution to this here equation, but that of course cannot apply here for the same reason I gave below. In a second experiment, slider 1 is given a velocity of 1 meters per second along the air track and collides elastically with another slider S3 that has mass n times that of S1 and is stationary. Show that, after the collision, the velocity of S1 is given by this equation here, and the velocity of S3 is given by this equation here. So, as before, we're going to look at this in terms of conservation of kinetic energy and conservation of momentum, with the added detail that we don't have the same mass anymore. Specifically, that the mass of S3 is n times that of S1. So let's start with conservation of energy. Our initial kinetic energy of S1 is going to equal the final kinetic energy of S1 plus our final kinetic energy of S3, where the mass is n times the mass of S1. Dividing out our half mass, and now noting that our velocity is 1 initially, we can rewrite this as 1. Now, to get this into an equation entirely in terms of V1 and n, I need to substitute out my V3. To do that, we're going to need more information, specifically from our conservation of momentum. We know that our momentum before is equal to the momentum afterwards of S1 plus the momentum afterwards of S3. Dividing our mass out, where we can just replace our V with 1, since that is our initial velocity. Now to solve this for V3, I'm going to subtract V1 from both sides and divide by n. And now I'm going to substitute this into that equation here. And that should let us find an equation for V1. Simplifying that down, and multiplying both sides by n to get it out of this denominator, and then expanding our brackets out. Simplifying this down, and also making it equal to 0. What we end up with is a quadratic, which I'm going to use the quadratic formula on, where this term here is our a, -2 is our b, and 1 minus n is our c. So our v1 is equal to our -b, which is 2, plus or minus the square root of b squared, which is -2 squared, which is just 4, minus 4 times A, which is 1 plus n, multiplied by C, which is 1 minus n. All of this is divided by 2A, which is 2 1 plus n. So we can firstly divide out the 2, and let's expand these brackets here. Simplifying that down, and that gives us solutions of either 1 plus n divided by 1 plus n, which is 1, or 1 minus n divided by 1 plus n, which is precisely what we're trying to show. Now to find V3, and I'm running out of room here. So we know from this equation here that V3 is equal to 1 minus V1 over n. So let's substitute our value for our V1 that we just found. Multiply the top and bottom by 1 plus n, and we'll see what we get from that. Simplifying that down, we get 1 minus 1, which is 0, and n plus n, because we have two minus signs there, which gives us 2n on the top. Dividing our n's out, we're left with 2 divided by 1 plus n, which is precisely what we're trying to find. In a third experiment, the sliders change roles so that S3 is moving at a velocity of 1 meter per second along the air track and collides elastically with S1, which is initially stationary. Use the answer from AII, and noting that S1 has a mass 1 over n times that of S3, show that after the collision, these two equations are true. So let's first consider how our equation was originally built. So our original equations from AII are these ones here. So to explore how these equations need to be changed to suit our new scenario, let's think about how they were constructed in the first place. So in our original scenario, we used our conservation of momentum. We used this equation here. Now, in our new scenario, the roles of S1 and S3 have changed. They've swapped around, which means that for our initial momentum, we're going to have the mass of S3, which rather than being m is nm. And finally, we just have our momentums of S1 and S3 respectively. Now, if we divide both sides by n, and you'll see why I'm doing this in a moment, we get the following. And now if we swap these two terms around, what we see is to get from this equation here to this equation here, we need to do two things. We need to swap V1 and V3, and we need to change n to 1 over n. Therefore, if we do it to these initial equations, we should likewise get final new equations for these terms. So let's now take our V1 here. We're going to swap V1 for V3, as we have dictated here, and we're also going to change n for 1 over n. Multiply the top and bottom by n, which is precisely what we're trying to show. Let's do the same for V1. So for V1, we're using this V3 equation here, because we're of course swapping them around. So let's replace our n with our 1 over n, and like in the last equation, I'm going to multiply the top and bottom by n, which gives me 2n over n plus 1, which, once again, is precisely what we're trying to show. Use the result of AII to show that if a massive bat is swung with a top speed of v meters per second to hit a stationary light ball in an elastic collision, the top speed of the ball is approximately 2v. And so in this case, our ball takes the role of S1, which is the thing that is being hit. And our velocity S1 is 2n over n plus 1. However, now, instead of having an initial velocity of 1 meters per second, we have an initial velocity of v. What that means is that all of our velocities are going to be scaled up by a factor of v. Which means instead of this equation here, we get this equation multiplied by v. Now, as the bat is much larger than the ball, we want to consider the scenario where our n is very large. This means that our v1 is going to tend towards 2nv over n because this plus 1 becomes insignificant. Our n's divide out, and we're of course left with 2v. In the reactor of nuclear power stations, fast neutrons with energies of about 2 MeV typically are produced by fission of 235 uranium. For a chain reaction to occur, these neutrons must be slowed down to energies of 1 electron volt or less by colliding with materials such as heavy water that contains hydrogen nuclei with an additional neutron. Calculate the velocity lost when these fast neutrons are slowed down. So we're looking at kinetic energies and we're looking at velocities, which means we want to use our kinetic energy equation. Since we're interested in calculating the velocity, we need to solve this for velocity. Now we're of course interested in the velocity lost, or the change in velocity, which is our initial velocity minus our final velocity. Substituting in our equation here. Now our initial energy was 2 MeV, and our final energy is 1 electron volt. Now to massage that a little bit to make it easier to type into the calculator, we can factorize out 2eV over m. Now if we put our numbers in, and that gives me 1.955 times 10 to the 7 meters per second. Using the results from parts A and B, explain why heavy water is used to slow down the fast neutrons, and suggest a reason why heavy water is used rather than common water. So let's do a bit of a throwback and look at what those sections actually told us. Bearing in mind that what we want is the velocity of the incident particle to be reduced as much as possible. So if we look at our B here, if we consider our neutron as striking something a lot more massive than itself, in this case in place of our massive bat, we see that the final velocity of our neutron is going to be twice the initial velocity, which is not at all ideal, since what we're trying to do is to reduce the velocity. We're trying to absorb the energy, slow them down enough that they're able to react. For our A, what we found is that if the masses are the same, if the masses are similar, then the velocity of our incident particle is completely absorbed. It goes to 0. What this means is that we want the masses of whatever our neutrons are hitting to be as close to the mass of that neutron as possible. Now, the best candidate for this is our H2O, because our two hydrogens in this molecule are quite simply just protons, ignoring the electrons because we're doing nuclear physics here. The problem is that our normal hydrogen with just the proton readily absorbs neutrons. It does so to become our deuterium, which is the component of our heavy water. The next best thing, therefore, is to make water, but instead of using just our stock standard hydrogen, using our heavier hydrogen. Or in other words, using our heavy water. Let me try and word that. Part A showed us that the greatest velocity reduction occurs when the masses are the same. The H in normal water fulfills this best, but also readily absorbs neutrons. The next best thing is to use heavy water with deuterium. Question 4. A parallel pair of fixed horizontal conducting tracks TA and TB lie in a uniform magnetic field B as shown. Track TA is divided by a switch on either side of which rest two identical metal wires, each of resistance R, that can slide without friction along the track. Initially, both wires W1 and W2 are stationary. With the switch open, wire W2 is given a short push to the right and then moves at a constant velocity v. Explain what occurs to the electrons in W2 as they move through the magnetic field. So if we consider a negative charge in our W2, because W2 is moving to the right, then so too is our electron here. If you use your right-hand rule, pointing your thumb in the direction of velocity to the right, pointing your fingers in the direction of magnetic field, which is into the page, then for a positive charge we will have an upwards force, but because this is a negative charge, we are going to instead have a downwards force. So the electrons will experience a downwards force. Explain why W2 slides along at a constant velocity. So let's consider the forces that are at work here. Well, we know that our charges, our electrons in this wire, are experiencing a downwards force. And since we're told that we can ignore friction, this downwards force is really the only one we need to consider. However, because it is downwards, it has no component in the direction of W2's motion to the right. This means it has no effect on W2's velocity, and since there are no other forces we've been made aware of, via Newton's first law, the velocity must stay the same. As the wire moves without friction and the force on the electrons is perpendicular to W2's motion, no forces act in the direction of W2's velocity. Its velocity, therefore, does not change. While W2 is moving to the right, the switch is snapped shut. Describe and explain the subsequent motions of both W1 and W2. So this leads to a very interesting scenario. If this switch here is indeed snapped shut, the motion of W2 results in a current flowing in this circuit. Now, since we have a current flowing in this wire now, if we apply our right-hand rule, we put our thumb in the direction of the current, our fingers in the direction of the field, then we see that our wire is going to experience a force to the right, meaning that it's going to accelerate. But now, because it is moving in a magnetic field, if we once again apply our right-hand rule, we have our charges which are moving towards the right, so point our thumb towards the right, point our fingers into the page, and we see that W1 is going to produce a current in this direction, in opposition to W2. So what's going to happen? We have our W2, which is inducing a current, and in doing so, it's going to lose energy and slow down, while at the same time, our W1 is going to be accelerating and speeding up. The reason it is speeding up is because there's a current flowing through it. However, as it speeds up and its opposing current increases, it will reach a point where its opposing current equals that of our W2 current. So at the point where our W1 and our W2 current equal, that is the point at which their velocities equal, there will be no current flowing through this circuit, and therefore there won't be any forces on the wires, at which point the wires are going to be moving at the same constant velocity. So let me go ahead and phrase that. As the switch is closed, W2's motion causes a counterclockwise current to flow. Since there is now a downwards current in W1, it experiences a force to the right, accelerating it. This motion causes W1 to produce a clockwise current in opposition to W2's current. As W2 loses energy to this process and W1 accelerates, there comes a point where their velocities equal and their induced currents exactly cancel. Since there is no current in the circuit, there is no force on the wires, and they therefore move at the same constant velocity. Determine the final velocities of W1 and W2. Explain your reasoning. So the best way to approach this situation is with conservation of momentum. Initially, we have our mass of our wire 1 times its velocity, and then afterwards we have both wires moving with the same mass, and we'll say moving with the velocity u, which they both share. The same masses and the same velocities. And that just gives us mv equals 2mu. If we divide our mass out, we just get that our velocity equals 2 times u. Or in other words, that our final velocity u is equal to v over 2, meaning that the velocity of the wires afterwards is half the velocity of that initial W1 wire. So let's try and phrase that. Due to conservation of momentum, the same momentum initially is now shared between twice the mass. As P equals mv, a doubling of mass results in a halving of velocity. Explain the energy changes that follow as a result of the switch being closed. So let's think about the energy before. The energy before is our half mv squared, our kinetic energy. As for our energy afterwards, we have our kinetic energy of both wires now, but at half the velocity. Half plus a half gives us a whole. And our divide by 2 squared down here gives us a 1 over 4. Which, as you might recognize, is half our EI. Half our half mv squared. So we can see that our kinetic energy has halved, which means we must have some energy lost. Since our wires are moving without friction, that only leaves the resistance of our wires, meaning that half of our kinetic energy initially has been dissipated as heat in the wires due to their resistance. Half the initial kinetic energy has been lost as heat due to the resistance of the wires. And that's it.